In this video, I'm going to talk about roaming. When a wireless client moves about, the expectations are simple. Good, seamless coverage wherever the client goes. Clients know how to roam between access points or APs, but they are ignorant about the wireless network infrastructure. Even in a large network, roaming should be easy, quick, and not disrupt the client's service. Cisco Wireless Network offers several roaming strategies. From your perspective as a wireless engineer, roaming configuration is straightforward. The inner working can be complex depending on the size of the wireless network as measured by the number of APs and controllers. As you work through this video, you will review roaming fundamentals, then learn more about how the Cisco wireless controllers handle client roaming and how to configure your controller to support it properly. Let me to review the roaming process. About the roaming, to understand how wireless roaming works, you should start simple. The following two sections discuss roaming between access points when no controller is present and when only one controller is present. Okay, more complex scenarios are covered later in this video or in future videos. First, let me to explain about the roaming between autonomous APs. Okay, in previous videos, we learned that a wireless client can move from one basic service set or BSS to another by roaming between APs. A client continuously evaluates the quality of its wireless connections. If the signal quality degrades, the client begins looking for an AP with a better signal. The process is usually quick and simple. Active scanning reveals candidate APs then the client selects one and tries to reassociate with it. This figure shows a simple scenario with two APs and one client. The client begins with an associate to AP1. Because the APs are running in autonomous mode, each one maintains a table of its associated clients. AP1 has one client and AP2 has none in this figure, as you can see. And after that, suppose that the client then begins to move into AP2 cell. Somewhere near the cell boundary, the client decides that the signal from AP1 has degraded and it should look elsewhere for a stronger signal. The client decides to roam and reassociate with AP2. This figure shows the new scenario after the roam occurs. Notice that both APs have updated their list of associated clients to reflect client 1's move from AP1 to AP2. If AP1 still has any leftover wireless frames destined for the client after the roam, it forwards them to AP2 over the wired infrastructure, simply because that is where the client's MAC address now resides. Naturally, roaming is not limited to only two APs. Instead, it occurs between two APs at any given time. To cover a large area, you will probably install many APs in a pattern such that their cells overlap. This figure shows a typical pattern when a wireless client begins to move. It might move along an arbitrary path. Each time the client decides that the signal from one AP has degraded enough, it attempts to roam to a new, better signal from a different AP and cell. The exact location of each roam depends on the client's roaming algorithm. To illustrate a typical roaming activity, each roam in this figure is marked with the dark ring. Alright, now let me to explain a little about the intra-controller roaming. In a Cisco wireless network, lightweight APs are bound to a wireless LAN controller through CAPWAP tunnels. The roaming process is similar to that of autonomous APs. Clients must still reassociate to new APs as they move about. The only real difference is that the controller handles the roaming process because of the split MAC architecture. This figure shows a two AP scenario where both APs connect to a single controller. Client 1 is associated to AP1, which has a control and provisioning of wireless access point or a CAPWAP tunnel to controller WLC1. The controller maintains a client database that contains detailed information about how to reach and